So, hello guys. Welcome to the first of hopefully a little bit of a short series on network fundamentals. So this will be a bit of an introduction into networking and a few of the basic concepts of how networking works to give you a bit of hopefully either an intro into the world of networking if you're thinking of going down that route, or to help you understand networking a little bit better if you are kind of technical but not really fully in depth with networking. So if you see or hear anything about networking, it can make a little bit more sense than it maybe did before. So the first session is going to be on the OSI model, and to give a bit of a background, the OSI model is purely theoretical, technically, but it's used to really give an understanding of the building blocks of a whole network stack, from all the way up at the application to then how we send the individual bits down a copper connection or a fiber connection, or waves over, radio waves over the airspace. So anyway, I'll start with a very generic discussion of, why do we need networks? I think that's a really good place to start when we're talking about, networking fundamentals. And so the real definition of a network is something, some elements connected together. And so in the case of computer networks, that is devices, that's endpoints, that's servers, that's routers in between to make sure that they connect together. That can be a range of different things, right? And originally those networks were set up to support university collaboration across borders. So you'd have places in America, in the UK, in Europe, maybe in Asia, all connecting together over a spanned network so that they could share resources and research information. So then they could make quicker findings, and they could support each other a lot better. Obviously, nowadays, the internet and networking is, effectively fundamental to life as we know it. IP networks are used for phone calls. So, while you use your phone and it sends radio waves to a local mast, 4G or 5G mast, from that mast, usually you'll use some kind of IP network to then convert and encapsulate it into a normal network packet. So then you can forward it along a service provider's network and then to another mast, where then it can be sent to the relevant person who you're trying to call. You've got video calls like what we're doing right now, Zoom, Skype, or Teams. You've got things like video on demand like YouTube. You've got banking, cloud apps, music, maps. A world of possibilities are enabled with the use of networks. And obviously a lot of those things that I just mentioned are summarized by calling the internet. But realistically, the internet is only one portion of networks across the world. You've got public and you've got private networks. And so public networks are, the things that anyone can connect into technically. And then you've got private networks, like, let's say, our office network, where we've got a range of devices that aren't publicly accessible, or at least not all of them, that only we can access when we're inside our local network. So you've got many different types of those networks. But obviously I'll be focusing on just networks in general. But I think it's good to have an understanding of what networks actually mean and what they look like before we actually get into the in-depth, maybe technical pieces. So as I mentioned, I'll talk about the OSI model. And as I mentioned, yet again, it's a theoretical view of a networking stack, all the way from an application down to the physical bits over some kind of media. And so it's nice to be able to separate what is at the application layer, which is more theoretical than the the networking portion, which is very structured, and you can actually see it within the within a packet capture or Wireshark capture. You can see the specific headers that mean certain bits of your layer 7 model. And so the way that it actually works with the layer 7 model is you will start at your application. The application will have some kind of data, and you will add some kind of control information or some kind of encapsulation to it, and then you'll pass it down the stack. So 7 will lead into 6, adding some more data, leading into 5, adding more data, and so on and so forth. And at each of those layers, that could be, some encapsulation, that could be some encryption, that could be any layer of control information. So you could be adding addresses, ports, some priority. You could be adding encryption, as I mentioned. It could be file format. So at these higher application layers, like 7, 6, and 5, you'll see that we'll be encapsulating data, the ones and zeros, with some kind of file format to make sense of that data, so that when we then pass it over the media, let's say copper, we have a set of high-low voltage signals. But when we actually get to that end host, that destination, it can use these headers or these control bits of information to actually de-encapsulate, or decapsulate, I should say, that information and make sense of what it actually means. It also means that we can have devices along the path from source to destination that don't really need to understand all the way up to layer 7, which means that they can be more efficient, they can be less resource intensive. So you take a simple layer 2 switch, it only needs to read these layer 2 headers, for example, and I'll get onto this a little bit later with more detail. But and then a firewall has to actually go through potentially all of these if it wants to do deep packet inspection. And specifically, the end host needs to have enough resources to be able to decapsulate all of these headers and understand every portion of it, so that it can make sense of that underlying data. Because if it can't do that, well, it can't understand the data because we haven't got the relevant control information. So anyway, I'll step through from layer 7 down to layer 1, and to give you a little bit of an insight on what each of these layers actually do. So we have the layer 7, and as I mentioned before, the first 2 or 3 layers are a little bit abstract. They're a little bit theoretical. They're less fact and specifics, and it's a little bit harder to visualize and understand. The network portions are a little bit more specific because you can do things like Wireshark captures and really see the specific structured data. So it might seem a little bit wishy-washy what I'm saying, but hopefully it kind of makes some sense. So the layer 7 is the application layer. So that is your application that transforms the data that you've just sent over the network into some kind of visual representation for a user. So it's really dealing with the interaction between the data that you're being sent and the end user, or the application doing some processing with it. So in this situation, you're watching a video, you're receiving bits or you're receiving data for this video. At the layer 7, we're translating that data into something that you can actually see on your screen and something that you as a user would understand, or hopefully understand. So that could be like a web browser using HTTP data. So it has to understand that HTTP data and then transform it into the actual page view that you actually see on your screen. Or it could be a photo editor, or a photo viewer. If you're getting the data for that actual photo over a network from a storage device, it'll be receiving that data and then transmitting, translating that data into something that the application can use. So that's what we do at the layer 7. It's really focused on what the application does with the data. We then have the layer 6 layer 6. And if you think about the way that the data flows, we're moving from 7 to 6. So at this point, or we're moving from 6 to 7, I should say. And in this point, if I take the example of a file, a picture from a network attached storage device, you're seeing, the JPEG format, for example, and you're understanding that, and you're removing per se the control information for that format, or you're de-encapsulating it so you understand and see the raw data behind that JPEG, for example. So it's basically understanding the file format and the format in which that data should look. Now, at this layer, we could also be dealing with compression. We could be dealing with encryption as well. So if we're sending it from an application to a destination, we're encrypting it, or we're compressing it, or we're adding some kind of file format. But if we're receiving it, well, we're de-encrypting it, we're decompressing it, we're trying to process that file format to understand the data. So that's where the layer 6 comes involved. And then we have layer 5. Well, we've got the data that we actually want to send across so that the end host understands it. But now we need to have some kind of understanding of a session. Now, that's mainly used in things like TCP, where you actually have session-based transmission from host 1 to host 2, for example, or source to destination. But the session layer can be important with other protocols as well. So it's really managing, I want to send this to this from source to destination, and it's understanding that state. So the layer 5 is really important. Like the firewall level, it's basically used in a situation where maybe you're sending an outbound request to a web server, get me bbc.co.uk. Because you want to see the news for some reason. The response from that server at BBC will come back through the firewall, and the firewall will say, well, did someone request this? Did someone request this data? Yes or no? In the case where it wasn't requested, well, then you drop that traffic because there's no session against that data. But in the case of requesting BBC's webpage, or homepage, I should say, the firewall will see that session and it will let it in. The same happens at the source and the destination. They'll manage that state and they'll say, okay, this session actually maps towards this protocol or this application. So I need to send it in this direction. And that also manages and starts to manage how we deal with ports, which are then used at the layer 4 layer. So this is all to do with, the layer 4 is all to do with transport. So it's how we send data over the network. It's how we communicate between the network portion and the application portion. So here you'll be dealing with things like ports, so source and destination ports. And those ports really are the transition between the network and the application. So it's saying this port on this IP address maps towards this specific application. So in the case of a web application on a web server, it knows that its IP address and port 80 maps towards this specific application. Might not be port 80, but that's an example. So at layer 4, we're also dealing with flow control per se. So we're trying to control how that data is put onto the actual network and sent across the network. So this layer is really important because in some cases, the likes of TCP, we want to be very specific about how we send traffic over that network. In the case of UDP, it's less useful, and I'll touch on this on a later talk where I actually go into a little bit more depth with TCP and UDP. But a spoiler, UDP will just send traffic. It doesn't have any kind of flow control per se. You can, at higher levels, more the application layer, control how UDP acts or how you send that traffic. But in a raw network stack point of view, layer 4 is really focused on that flow control. So if you use UDP, well, it's not going to do any buffering. It's not going to do any congestion avoidance. It's just going to send the traffic and hope that it gets there. So at this layer, we're really interested in how that traffic goes across the network. So we also deal with segmentation as well at this point, because we want to make sure, well, the data stream that we're getting from the application, maybe that's a constant stream of RTP data. And in that case, RTP, video protocol, media protocol, it wants to send traffic as effectively as quick as possible and reliably. So maybe we'll be getting data in a constant stream at a constant rate. And layer 4 is really in charge of taking that data and segmenting it as well. So it's knowing how to chunk up that data because in some applications, like RTP, we want to send that data as quick as possible. You know, we want to take in the data that we just got from the application and segment it up and pass it down the network stack as quick as possible. In other cases, you know, let's say a file transfer, it will want to wait for the largest possible segment that it can handle and then send it down. And by having that larger segment, it's a little bit it induces a little bit more latency / delay. But it does mean that the actual bandwidth and the actual data transmission is a little bit more what's the word, efficient, where, because when you send some data, you have your data portion. Maybe that's 1,000 bytes, maybe that's 5 bytes. But on that 5 bytes, you've got a fixed header for each of these layers. So, you know, you've got the next layer, layer 3 and layer 2, and also the layer 4 layer when you're in the network portion, when you're sending traffic over the network. All of those layers beneath are going to be effectively, usually, relatively fixed, regardless of whether you're sending 5 bytes or 1,000 bytes. Now, if you're sending 1,000 bytes versus 5 bytes, or you've got a percentage of overhead compared to the actual data that you're sending. So in applications where, you know, latency or delay isn't too important, you'd want to really fill up those segments and make them as big as possible. So then you're more efficient with the data and the bandwidth that you have, and also the processing, right? Because the more individual packets that you send, the more processing downstream and the more processing on your sending and receiving device that you have to do. Because for each one of those segments that you send, some device along the chain may have to process it. The end host will have to process that as an individual segment. Whereas if you send one large segment compared to 10 smaller segments, that's one packet versus 10 packets that you have to process, which can sometimes make a difference in performance and resource utilization. Now, obviously, I'm being very generic here. It really does depend on your situation and the application and the protocol that you're using as to, you know, what's most appropriate. I can't blankly say, you know, RTP or something very specific has to be this size, because it really does depend on your application and your use case. But from a generic point of view, those are the kind of concerns that you have to think about when you're dealing with a network. You know, you want to think, how big do I need those segments to be versus the delay and the overhead of those packets that we're sending. And we're also, in some senses, looking at congestion avoidance. So at this layer, we're dealing with certainly with TCP, right? We're dealing with some advanced control information to make sure that we can do these advanced things like congestion avoidance, like flow control, and making sure that we're sending at the right rate rather than just, you know, throwing it down the stack and letting the network deal with it. We're trying to rate limit and say only send this portion, only send that portion next, and so on and so forth. So that's the transport layer. It's really focused on flow control and how we manage the data between the application and the network. It's really that border between the two. So moving on, we've got then layer 3, which is the network layer. And that is intended to effectively be the control information and the control management for sending a packet from this device across the whole network between me and the destination. So that might be, you know, that BBC server that I mentioned. Now usually there are some hops in between the two, which will mean that some bits of that control information will change. So if you've ever heard of network address translation, that will change some attributes of your layer 3 control information to make relevant changes to it, so that the local network portion, you know, an ISP's network, or your local office network, or the BBC network managing those servers, can really understand the layer 3 information a little bit better. That's a little bit out of scope of here. Really what you want to focus on here at layer 3 is remembering that the layer 3 is really end-to-end across the network. And that's the concept here, is that it should be allowing a network between your host, your source, and your destination to make the right decisions on the way that that packet will be sent and the direction that it's going to be sent. So at layer 3, we're dealing with routers and routing. So that can be dynamic or static. And those routers, those intermediate hops, need to understand, well, I've got this IP address, I've got this specific destination IP address. Where can I reach that? And routers will have a thing called a routing table, which will say this specific prefix or this specific network or IP address is reachable behind this specific interface. And that's where layer 3 really comes into play. It's making sure that you can go down the right path to reach your destination. So you can think of it as an address, a postal address. It can be broken down into your country, your town, your road, and then your actual door number, for example. Or it could be imagined as a postcode. You've got, for example, in my case, RG12, which is, as far as I understand, Bracknell. And then you've got those 3 or 4 different characters after that, which then start to break Bracknell, for my example, down into smaller segments. So you've got a very generic area of Bracknell. Maybe it's the south of Bracknell. And then inside south of Bracknell, you've got then smaller segments and smaller segments and smaller segments to really then, effectively in the postal code situation, identify a specific road where that destination is. And that's very similar to IP addressing. When we come on to subnetting in a different talk, a later talk, that'll make a little bit more sense, because you have the concept of a subnet or a range of addresses that are under someone's specific ownership. And so there is a standard per se, or a recommendation for those at least public IP addresses to be assigned in a certain way, so that we know this block of addresses is assigned to this country or continent, and then this block of addresses is for this customer or company or government organization, and so on. That's getting a little bit too in depth, but hopefully that kind of idea of the postal address really explains how those addresses might work, and how we can take that across a network. So if you think about, you want to go to someone in Birmingham, you have their full postal address. Well, you need to go to Birmingham first. So you go to your first hub, you go to your first junction. Well, which direction is Birmingham? Oh, okay, it's straight on. Keep on going straight on. You go to the next portion. Okay, well, I'm almost there at Birmingham. Which part of Birmingham do I need to go to? So you're at the next junction. Okay, do I go to the first junction, first exit of this roundabout? Do I go to the second? And so on and so forth, till you actually end up on the relevant street or road for the place that you're going to. It seems like a little bit of a corny explanation, but I think that's probably one of the best real world examples of how you can break those down, and how the IP addressing helps in understanding how you can get to your destination. So as I mentioned, layer 3 is really focused on that network portion. It's getting from your local network to your remote network, your destination network. Next, we have layer 2. And layer 2 kind of is similar to the network layer, but it's relative to your local network inside what's called a subnet, or your local network. So you can imagine this as how do you get towards your home router inside your home network? Maybe if you're connected via a normal cable, or you're coming in on a specific port, well then how do I what port do I leave from that switch to get to the actual external world or the router? And so this is all controlled using what's called media access control addresses, or MAC addresses. And those are intended to be unique per physical interface on a device. They're basically built up of 2 separate unique segments of the address. So you've got one portion which is for the company or the manufacturer to specifically define. So, for example, Cisco, Juniper, Arista, Asus, whoever else, any company that is creating some kind of network capable device will have an assigned segment for their company and their devices that they make. And then the final segment is supposed to be unique. So Cisco will have an identifier, but then that last segment of the MAC address is then for Cisco to uniquely identify that specific device, or in my case, Asus, to specifically identify this laptop that I'm using here to present to you guys. And with inside those addresses, we have a source and destination address when we're sending over the network. And so what that allows us to do, if we have some kind of a layer 2 device in between, my laptop and the next device along, it's basically saying we have, if we have an intermediate layer 2 switch, it's helping that switch know where I want to go inside the layer 2 domain. And what this means is that layer 2 switch that I interconnect between my laptop and the router, the office router that connects to the wider internet, is basically allowing that to be less resource intensive because it doesn't have to decapsulate as much information as a normal router. And it can just then identify, okay, this physical address is behind this port, but that's all I need to know. I don't need to know the full routing path. I don't need to know anything more than just my local area network. And so this is really important where you have network segments where there are multiple devices connected. If you're connecting back to back or straight direct from my laptop into a specific device or into the router, into a layer 3 enabled device, MAC addresses aren't really utilized. They're not. They obviously are used, but when you're sending the packet, when you're sending the data, but they aren't actually used along the path from your source to the destination, because you're going from one very specific source across the cable to another device. And there's no ambiguous decision there to say, well, do I need to go that way or do I need to go that way? It's very much, it goes from point A to point B. Now you contrast that with, let's take our office. We've got X number of laptops and devices connected into a layer 2 switch, which is then connected into the office router, which then can forward you out onto the internet or to a different part of the network. And it's making sure that your laptop can reach towards the router via one specific port, in our case. So that's why we need that. And it's making sure that, when the switch gets my information, when my switch gets my packets destined for the internet somewhere, it doesn't then go and send them to, Mark's laptop, for example. It actually sends them via the right direction. Now, if you didn't have those addresses, that layer 2 switch would then just flood blindly out of all ports in an attempt to get your traffic to the right destination. Now, in a real world example, you can imagine that trip to Birmingham, you've hit a junction, you've hit a roundabout, and you need to know which exit of that roundabout you need to leave on. Maybe only one of those, exits only points towards Manchester, towards Birmingham. Maybe another one points towards Manchester, maybe another one points towards London. So you want to make sure you go down the path towards Birmingham, right? You don't want to go down the path towards Manchester, because otherwise you'll go to the wrong place. Maybe you can figure it out once you've passed that junction. But in the world of networking, we want to make sure that we're going in the right direction. So this is why we use these MAC addresses, to make sure on our very much our local network, we go in the right direction. And I've very much specifically talked about MAC addresses, but at layer 2, you do have other technologies, and these are relatively legacy now. The main technology that we use is Ethernet. But back in the day, well before my time, there used to be things like frame relay and ATM and plenty others that I don't remember from my CCNA. And those use different formats and encapsulation compared to Ethernet. So we have MAC addresses within inside Ethernet, but we'll then also have other identifiers or IDs or whatever you want to call them with inside frame relay, with inside ATM, or any other layer 2 protocol. But it's always taking that same kind of similar concept. It's knowing on your very local network what direction you need to go. Do I need to go in that path or that path? So that's the layer 2, and it's, as I mentioned, it's really about your local connection and how you actually get to that relevant destination. We then have layer 1, which is very much the physical layer. It's the ones and zeros, it's the raw data. So you've got all of this control information from these relevant layers, and you've also got your actual data that you're trying to send to your destination. But now it has to go over the physical media, whether that's copper, whether that's fiber, Wi-Fi, radio signals. We need to translate that actual data that you've got on your device to something that can be sent over your physical media. So in the case of a copper link, well, that's voltage peaks and troughs. So that's a high voltage signal or a low voltage signal. You've got fiber optics, so that could be a burst of light. Dial-up, well, that's signal tones across the telephone line. Wi-Fi, that's, as far as I understand, radio waves, and so on and so forth. I could go through different types as well. But it's translating that computer understood data into something that can transmit across some kind of media connecting to devices. So that's the OSI model, and yeah, that's the end of that. Now, it's really important. I'll just come back to this diagram because I think it nicely explains it. We're taking from a source, we're going through all of those relevant layers, from 7, 6, 5, so on and so forth, and adding control information along the path. Now I come back to that idea of a layer 2 switch. A layer 2 switch doesn't have to be as as spec'd out as an end device or a firewall, because it only needs to take that traffic, that data up to layer 2 to process the layer 2 control information, and then pass it back down to layer 1 again and pass it on through the network. A router might then come along and it has to take it up to layer 3 just to understand the layer 3 information. It then re-encapsulates with the layer 2 and then passes it down the physical media on layer 1 and then onto a firewall, which might have to process all of this. It might have to go and do a deep packet inspection, and then it needs to be able to decapsulate all the way up to layer 7 potentially to understand actually what is the content of that message that you've sent. Is it just a picture of someone's wife, or is it, is it a virus that you're trying to send? And so that's why you have different categories of devices and different specifications. Our firewalls here in the office might not be spec'd to be able to do layer 7 inspection. I'm not sure. I can't remember off the top of my head. But I know that those more modern devices, which have a lot more processing power, can go all the way back up to layer 7 to decapsulate everything and then re-encapsulate everything based on the information that it's already had and that it's already read and understood from those control information headers. And so obviously then right at the end, you've got the end host, which should have all of the capability to go all the way back up to layer 7 and decapsulate all the way. So that's why we have these layers, to really understand where you need to be at for your device and what bit of information it needs to understand, so then it can make a decision to forward your traffic if we come back down to the networking portion. So that's all for today. That's the session on OSI layers and the model. Hopefully that gives you a bit of an understanding of what the fundamental building blocks of networks are. And hopefully it gives you an appreciation, at least for a normal networking stack, and how much additional control information actually goes into sending a packet across a network. As you can see, there's quite a bit that goes into it to make sure that everything works as expected. So as I mentioned, this is a series of talks. There's going to be another one next, which will be, I'm not exactly sure what it'll be, but it'll be another fundamental networking technology. So keep an eye out for that, and hopefully this has been useful. Thank you very much.